Hello students, welcome to EPG Pathshala. I am Professor P03 from the University of Jammu. Today we are going to discuss about a module entitled as Vapor and Solid State Growth under paper crystallography and crystal growth. In this module we will learn about the basic background of crystal growth from the vapor, that's the gas phase. There are two categories of this method of growth. One involving closed system techniques and the other system methods. The closed system techniques are explained. Unseeded growth of chemical vapor deposition and the arrangement used in this type of growth is described. Seeded crystal growth by chemical vapor deposition method is also described. Deposition from the vapor phase is a technique which is performed in the fabrication of thin layer of metal, insulators, and semiconducting materials. Different types of achieving growth from vapor phase include 1. Sublimation, 2. Vacuum evaporation, 3. Molecular beam epitaxy, 4. Temperature oscillation method, 5. Gas transport processes, 6. Halide transport processes, 7. Chemical vapor deposition, and 8. Vapor phase epitaxy are explained. Systems in vapor phase growth under physical vapor deposition process and those under chemical vapor deposition, abbreviated as CVD process, along with some examples are classified, and this summary is given. Basic background of vapor phase growth, giving description of some fundamentals regarding important techniques like growth by sublimation, growth by chemical reaction, and transfer technique is described. Growth from solid state involving annealing techniques, namely strain annealing, zone heating, sintering, and hot pressing is explained. Layer growth from solid phase, also known as solid state epitaxy, is also described. Now growth from the vapor phase. See, there are methods of growth in which the materials from which the crystals have to be grown are transported to the growth zone as volatile compounds which react or decompose to give the material and a byproduct. The methods involved fall in two categories, namely closed system techniques and open system methods. Closed system techniques. In closed systems, the byproduct is recycled. Let us consider a typical equation of the type twice O solid plus Y2 in the form of gas leads to twice OY gas at temperature T plus delta T leads to twice O solid plus Y2 in the form of gas. Here O represents the material to be grown as crystal and Y is used as an agent for transportation. The superscript specifies the state of the various species. Capital T represents the temperature of the nutrient zone. T plus delta T is the temperature of the growth zone, which may be positive or negative depending on the sign of the heat of reaction. Delta T is the temperature difference between the nutrient and growth zones. If Y2 diffuses in a closed system from the growth zone to the nutrient zone, only a small amount of Y2 is required. If it is an open system, there would be a flow of gas through the growth region where reactions take place, such as 2OY gas leads to twice O solid plus Y2 in the form of gas, or twice OY gas plus H2 gas leads to twice O solid plus twice HY. The vapor phase process has a slow growth rate averaging less than 10 raised power minus 4 centimeter per minute for single crystal growth, whereas it is about 10 raised power minus 2 centimeter per minute for growth in case of growth from molten phase, that is the melt growth. However, better perfection and control on thickness, composition, stoichiometry, and doping in vapor phase epitaxial growth, that is VPE growth, makes it superior for the growth of active layers which actually perform electronic functions. Vapor phase techniques are also very useful in the deposition of metal films required for solid-state device and integrated circuit fabrication. There are a variety of vapor phase systems which have been developed. However, two major categories are PVD and CVD. While PVD category involves both vacuum evaporation and sputtering. In case of vacuum evaporation, the required thermal energy is supplied by resistance or electron beam heating of the source. In the case of sputtering, the source material is transformed into the vapor phase by ion bombardment of a source electrode, that is the target. There are so many variants of growth from vapor phase that it may be beyond the scope of this text to provide details of all of them. However, it is better to be knowledgeable about the title of various types of growth from vapor phase, which may be summarized here along with some of the several crystals that have been grown. Systems under vapor phase growth are indicated in figures 33.3 A and B. The relevant details are summarized in the form of charts in these figures. The figures provide examples of most common transport agents and deposition of materials. While this cannot be claimed to be an exhaustive list, it does serve the purpose of providing some initial information regarding usefulness of the techniques. Example of closed system. We may take up the example of producing material samples for research where use is made of a halide transport process in a sealed silica tube. In this case, the material of which the crystal as grown is desired is placed in a tube along with enough of halide so as to produce 1 atmosphere pressure at the growth temperature. The tube is sealed and then put in the multi-zone furnace. One end of the sealed tube contains nutrients, which is heated to a higher temperature than the other end, at which the growth of the material as crystal is desired. In the case of materials having higher melting points, the nutrient zone is maintained at about a temperature which is 50 to 150 degrees centigrade more than the temperature at the growth zone, which may be around 800 to 1200 degrees centigrade. It may take around 6 to 40 hours before one succeeds in the growth of hardly few small crystals. This is known as unseeded growth of chemical vapor deposition, and the arrangement is as shown along with the temperature profile in figure 33.1. A better production method is to make use of seeded chemical vapor deposition technique of growth as is shown in a schematic diagram of figure 33.2. In this arrangement, the seed is used in a furnace with temperature gradient as shown. Here the nutrient is placed in the lower end, which is kept hotter, and the seed is placed at the upper end, which is a cooler region. There are different ways of vapor phase growth. Deposition from the vapor phase is a technique which is preferred in the fabrication of thin layers of metal, insulators, and semiconducting materials. There are different ways of achieving growth from vapor phase which may be put as under: growth by sublimation, growth by vacuum evaporation, growth by molecular beam epitaxy, growth by temperature oscillation method, growth by gas transport processes, growth by halide transport processes, growth by chemical vapor deposition, growth by vapor phase epitaxy. Figure 33.2 shows schematic diagram in which arrangement for a seeded crystal growth by chemical vapor deposition method along with the temperature gradient maintained in the system is shown. Cool region is above the hot region. Physical vapor deposition, which is abbreviated as PVD, and chemical vapor deposition, abbreviated as CVD, are both used widely for the deposition of polycrystalline oxide and metal films on parts of any assembly or improvement of mechanical and structural properties, corrosion, and abrasion resistance. It becomes possible on account of the fact that vapor phase deposition can be done on irregular shaped substrates, inside surfaces, and besides offering maximum control of materials properties such as thickness and composition. The vapor phase process has a slow growth rate averaging less than 10 raised power minus 4 centimeter per minute for single crystal growth, whereas it is about 10 raised power minus 2 centimeter per minute for growth in case of growth from molten phase, that's the melt growth. However, better perfection and control on thickness, composition, stoichiometry, and doping in vapor phase epitaxial growth, that is VPE growth, makes it superior for the growth of active layers which actually perform electronic functions. Vapor phase techniques are also very useful in the deposition of metal films required for solid-state device and integrated circuit fabrication. There are a variety of vapor phase systems which have been developed. However, two major categories are PVD and CVD. While PVD category involves both vacuum evaporation and sputtering. In case of vacuum evaporation, the required thermal energy is supplied by resistance or electron beam heating of the source. In the case of sputtering, the source material is transformed into the vapor phase by ion bombardment of a source electrode, that is the target. There are so many variants of growth from vapor phase that it may be beyond the scope of this text to provide details of all of them. However, it is better to be knowledgeable about the title of various types of growth from vapor phase, which may be summarized here along with some of the several crystals that have been grown. Systems under vapor phase growth are indicated in figure 33.3a and b. The relevant details are summarized in the form of charts in these figures. The figures provide examples of most common transport agents and deposition of materials. While this cannot be claimed to be an exhaustive list, it does serve the purpose of providing some initial information regarding usefulness of the techniques. Figure 33.3a shows number of systems in vapor phase growth under PVD process. For example, physical vapor deposition, that's PVD process, is bifurcated into two: vacuum evaporation and sputtering. In vacuum evaporation is included reactive, that is compounds having volatile elements. Second, direct evaporation means metals, alloys, semiconductors, and MBA for, that is molecular beam epitaxy for semiconductors. Next is sputtering. It has two types, direct and reactive. In direct, we can have alloys, metals, and compounds. In reactive sputtering method, there are compounds having volatile elements. Figure 33.3b shows number of systems in the vapor phase growth under CVD process, that is the chemical vapor deposition process. Now we shall discuss basic background of vapor phase growth. The basic background of growth from the vapor phase, that is the gas phase, may be summarily described here. Materials which decompose or sublimate before melting at atmospheric pressure and for which there is no suitable solvent can often be grown from the vapor phase. In comparison with other growth techniques, this method is much complicated for the growth of large crystals. Supersaturation can be relatively controlled more easily as compared to growth from melt. The growth process can be defined in three stages: transport of material, surface reaction, and dissipation of heat. A very brief description of some fundamentals regarding important technique of crystal growth from vapor phase may be given here. Growth by sublimation. In this method, the substance is converted directly from solid to the gas via liquid phase. The substance from the gas phase is now converted back to the solid phase without intermediate liquid state. The process is frequently carried in high vacuum, and heating or cooling of the said crystal or area where the growth initiation is desired is often required. Formation of ice crystals in nature occurs in this way. Growth by sublimation. In this method, the substance is converted directly from solid to the gas via liquid phase. The substance from the gas phase is now converted back to the solid phase without intermediate liquid state. This process is frequently carried in high vacuum, and heating or cooling of the said crystal or area where the growth initiation is desired is often required. Formation of ice crystals in nature occurs in this way. Next is growth by chemical reaction. In the growth from gas phase, using chemical reaction, the material to be grown is prepared right in the growth region. For example, in the formation of silicon carbide, SiC, a volatile silicon-containing substance such as silicon tetrachloride, SiCl4, and a carbon-containing substance such as toluene, having chemical composition as C7H8, are each vaporized in a separate inert gas stream and brought together in a heated zone where the two react, giving silicon carbide, SiC, and other products. An important application of this technique is the epitaxial growth of silicon. This is obtained from silicon tetrachloride upon reaction with hydrogen gas as per the equation SiCl4 plus twice H2 gives Si, means silicon, plus 4 times HCl. The silicon so obtained is made to deposit an additional layer of silicon on a heated silicon crystal, giving rise to the epitaxial growth. Such silicon crystals are used in the construction of transistor devices. Transfer technique. This is also an important process of crystal growth from gas phase. The technique is performed in a closed and sealed quartz tube with silicon feed material at one end maintained at 1100 degrees centigrade and silicon seed crystal at the other end maintained at 900 degrees centigrade. A small amount of iodine is added before the tube is evacuated and sealed. Iodine reacts with seed silicon as Si plus I2 gives us SiI2. At the lower temperature of the seed region, SiI2 decomposes to form SiI4 with the growth of a crystal as twice SiI2 gives us SiI4 plus Si. The product SiI4 moves back to the feed region to produce more SiI4 by reverse reaction, that is SiI4 plus Si gives us twice SiI2. Growth by this process is very slow and also difficult to control. Greenockite, that is cadmium sulfide, silicon carbide, that is SiC, and verticide, that is ZnS, have been grown by this technique. These techniques have been frequently used for the growth of organic crystals, metal crystals, and semiconductor materials such as silicon. Chemical transport methods are widely used for the growth of semiconducting, insulating, and magnetic crystals using closed tube arrangements. As for example, crystals of most adamantine compounds could be grown in sealed quartz ampoules. About 5 mg per cc of I2 are added to a powdered charge of the compound in vacuum. Crystals grow at the cold end of the tube as is shown in figure 33.4. In this method, iodine transports the non-volatile metal atoms by formation of an iodide which is volatile at low temperature and which then decomposes in the region at high temperature. The whole process is carried out in directional or a two-zone furnace. The tube is tilted by around 10 degrees centigrade to promote convection. Though the seed tube methods are very useful in research, but they are very costly for production. Open tube methods are preferred for production purposes using gas phase reactions. Now let us now discuss solid state growth. You see, growth from the solid state is because of atomic diffusion, which is very slow in many cases. However, in certain exceptional cases involving superionic materials, some cations are quite mobile. On account of its limitations, solid state growth techniques are not very commonly used, especially when there is an option for growth by other techniques. The metallurgical processes, including annealing, heat treatment, sintering, and quenching, assume great importance in tailoring the properties of materials. The growth of single crystals, either from polycrystalline or amorphous solids, has certain advantages and some disadvantages. The advantages are its simplicity. It is necessary to anneal the sample. Thirdly, possibility of avoiding contamination as no solvents are used and the sample has very limited area of contact with foreign materials. However, it has certain disadvantages also, which may be summarized as follows. Number one, it lacks reproducibility. Number two, there are difficulties in attaining high perfection materials. Number three, some crystallographic defects are unavoidable in spite of all care in processing. Prior to development of techniques like float zone, refining and cold crucible techniques, solid phase growth was being extensively used in the production of pure single crystals of melts. Now we shall talk about annealing techniques. There are two main techniques: strain annealing and zone heating. Now let us take up strain annealing. Cold worked metals show more grain growth than unstrained samples. It is observed that a critical strain induces nucleation and growth of new grains, a process known as secondary recrystallization. Below the critical strain, only primary crystallization takes place. Above it, several new grains nucleate and grow. Temperature gradient strain annealing using a two-zone furnace has been successfully used in causing one grain to grow down specimens of copper, aluminium, lead, and tin. This technique is named as grain boundary migration technique. The next is zone heating. By this technique, metals like tungsten and molybdenum in the form of single crystal wires are produced. Figure 33.5 is a zone heating arrangement. The wire is electrically heated in vacuum and a small traveling heater passes a hot zone up and down the wire. In this way, whole length of the material can be grown into a single crystal. Shows two figures, 33.5 and 33.6. 33.5 is a schematic diagram showing zone heating arrangement for the production of single crystal wires, whereas figure 33.6 is a schematic illustration of the growth of thin layers from solid phase, the process shown in sequential order. Sintering and hot pressing. It involves the process of annealing of a pre-compressed powder known as sintering. The process of annealing of a powder under pressure known as hot pressing is also used here. Both these processes are used for homogenization of alloys and grain growth. Both these techniques have been used in metallurgy for production of ingots and shaped components of difficult alloys. However, these are complicated processes but do not offer any scope for the growth of good crystals. Thin layer growth. The growth of thin layers from solid phases, popularly known as solid-state epitaxy, is a technique which has recently generated a lot of interest. Both amorphous and polycrystalline materials can be crystallized at high rates. Ion implantation is used to make semiconductors amorphous, which results into formation of layers having high resistivity. These layers are selectively recrystallized by using energy beams, resulting into conducting patterns. One is able to achieve growth of nearly isolated crystalline layers by using standard lithographic and etching process to create a hole in oxide on a particular substrate, followed by depositing amorphous or polycrystalline material from plasma. A stripe of crystal is grown by starting at the hole site and traversing a laser beam. The process is shown in figure 33.6. Here the figure shows an oxide layer on a crystalline substrate. Amorphous or polycrystalline film deposition is then made. A stripe of crystal is then grown by using a laser beam. This process is sequentially shown in figure 33.6. Let us now summarize of what we have discussed so far. Systems in vapor phase growth under physical vapor deposition process and those under chemical vapor deposition abbreviated as CVD process, along with some examples, are classified and this summary is given. Basic background of vapor phase growth, giving description of some fundamentals regarding important techniques like growth by sublimation, growth by chemical reaction, and transfer technique is described. Growth from solid state involving annealing techniques, namely annealing, zone heating, sintering, and hot pressing, is explained. Layer growth from solid phase, also known as solid state epitaxy, is explained. Thank you.